Welcome back. Welcome back. So today we're going to do section 10.3, which is polar coordinates. That's another coordinate system. And for some of you, this will be completely new material. Okay, so let's recall what you have with rectangular coordinates. So if you're given a pair of coordinate axes, x and y, a point, AB, is A units along the x-axis, B units along the y-axis, so we'll have coordinates A and B. So that is the classical rectangular system of coordinates. Every point has a unique coordinate, which is the distance to the x-axis and or actually the projection onto the distance to the y-axis if you're in the first quadrant. Okay, so now what about polar coordinates? That's a completely different coordinate system. Instead of x and y axes, you have something called the polar axis, which is the horizontal axis. And then you have a polar angle. So here is the idea. A point in the polar plane is specified by two pieces of information. The distance to the origin, which is called r. So that's the distance to the origin, and the angle that the ray given by the distance to the origin makes with the polar axis. So a point in polar coordinates is given by a pair r and theta. And here, since r is a distance, r is going to be at the beginning at least greater than or equal to 0, and theta is an angle, any angle. Okay, now note that a point is not unique in polar coordinates. There are many, many representations of a point in the polar plane. So if a point is P, specified by r and theta, well, if I add 2 pi to theta, I will get the same answer, the same. So there is more than one way to represent a point in polar coordinates. Okay, so now it is convenient to allow for negative r, negative values of r. So how do we interpret that? Well, suppose I were to flip the this this segment over through the origin, then we're going to interpret this point here as being minus r comma theta. So that is the point that is diametrically opposite to the point P. So it is fairly clear from this description that minus r comma theta is the same thing as taking r comma theta and taking theta and adding 180 degrees to it, which is an angle of pi. So minus r theta is the same as r theta plus pi. This allows you to define, this is a definition, this allows you to define polar coordinates with negative values of r. Okay, so let's do an example. So what about the point 1 comma pi over 2? What is that in polar coordinates? Well, that is the point that is distance 1 to the origin and makes an angle of pi over 2 with respect to the polar axis. So that's this point here. This is 1 pi over 2. In other words, 1 pi over 2 in polar is equal to the 0.01 in rectangular. Here's another example. What about the point 1 comma pi? Well, that would be an angle of pi, one distance, unit distance to the origin. So 1 pi in polar is corresponds to, or I should write corresponds, not equals, corresponds to the point which is minus 1, 0 in rectangular, because an angle of pi rotates around once. Okay, so what I'd like to do is talk about how to convert in general between polar and rectangular. That's fairly simple. Let me, though, clear the screen. So first of all, if you have, so this will be conversion formulas. So if you have a point, x, which is given by xy in the rectangular coordinates, then we can form a following triangle. X is the one leg, y is the other leg, and then we have the square root of x squared plus y squared, but that's the distance to the origin, that's r. And theta is this angle in the right triangle. So from this, we immediately get that x is equal to r cosine of theta, and y is equal to r sine of theta. And this is the way to go from polar to rectangular. If you know the r and the theta, you know x and y. So for example, what if we wanted to know how to rewrite the point, oh, I don't know, 1 comma pi over 3 in polar. I want to convert that to rectangular. So that would say that x is 1 times cosine of pi over 3. So that's a half. And y would be 1 times sine pi over 3, which is going to be square root of 3 over 2. So the point would be square root of 3 over 2, 1/2 in rectangular. Okay, so how about going the other way? Well, we know that r squared is x squared plus y squared, so we can compute r by taking the square root. And we also know that tangent of theta is opposite over adjacent in the right triangle, so that's y over x. From this, you can calculate the theta by taking the arctangent of y over x. So this is going to go from rectangular to polar. Okay, so those are the basic conversion formulas. So the next topic is to talk about polar curves, and this is, we're going to spend some time doing this. Yeah, let's see. So polar curves. So most of the polar curves we deal with are the form r equals f of theta, where f is a function. So that's, let's do some simple examples first. So let's consider r equals 1. What does that mean as a polar curve? What this means is this is the set of all pairs r and theta such that r equals 1. So theta doesn't matter so much. Theta doesn't matter at all. We're looking at all points a unit distance to the origin, so that's a unit circle centered at the origin. Okay, that's pretty simple. What about this one here, though? Theta equals pi over 4, let's say. Well, that's a set of all, oops, that's bad. That's the set of all points of the form r comma pi over 4 in the polar plane. Well, what should that mean? That means the angle is always the same. The angle is always pi over 4. It's just the distance to the origin which changes. And this is a line. It's a line of slope 1 through the origin. Okay, slope 1. Well, that was fairly simple. So let's consider something more complicated. How about r equals the cosine of theta? Now we get into like manipulation of the equation because there's no way to guess the answer from just looking at this. We have to manipulate it. So one thing we can do is we can multiply by r. So you get r squared is r cosine of theta. Now r squared is x squared plus y squared. I'm converting this to rectangular now. And the right side is x, because x is r cosine of theta. So x squared plus y squared equals x. Well, what's that? Well, it's easier to write it in the following way. X squared minus x plus y squared is 0. And now I'm going to complete the square of the x's and the y's. The y's are already square completed. So this is going to be x squared minus x. The coefficient of x is -1, so -1 over 2 is -1/2. We square it, we get a quarter. So it's x squared minus x plus a quarter plus y squared. Well, if we added a quarter to the left side, we better add a quarter to the right side. And this is x minus 1/2 quantity squared plus y squared is a quarter, which I'll think of as a half squared, because this is then going to be a circle of radius 1/2 centered at the point 1/2 comma 0. So the picture of this circle is this. Here's the point 1/2 comma 0, and we have a circle of radius 1/2 centered at that point. That's my circle. Okay, and I've drawn this in rectangular using a pair of axes. Okay, so that's the example. Well, these examples are all fairly easy. Now we get to the more complicated kinds of examples, and let me clear the screen. Okay, so the next example is of the form r equals 1 plus the cosine of theta. Okay, so we have r equals 1 plus cosine theta, and it'll be, in order to plot this, it's very convenient to first of all figure out the values of r in terms of theta in some rectangular sense. So let me put a theta axis here, and let's put 1 plus cosine of theta vertically. So let's graph that for theta between 0 and 2 pi. So as theta starts off at 0, r is 2. So at 0, and at pi over 2, it's decreasing. See, what we have to understand is where it's increasing and decreasing and positive and negative. So it's going to decrease the value of r as theta goes from 0 to pi over 2. At pi over 2, it has value 1. Now, what about at from pi over 2 to pi? It continues to decrease. At pi, it has value 0 because cosine of pi is -1. So it's going to go like this. And then from pi to 3 pi over 2, it's going to start increasing again. And then at 2 pi, it's going to be back at the maximum. Then it'll start repeating itself. Okay, so this is not what we want to graph. We want to graph the polar equation. So let me put in the polar plane. This is the polar plane. So now the way we're going to deal with this is start off at theta equals 0, and we're going to be staring the whole time at the values of theta, which are decreasing, increasing, positive, and negative. And here, nothing is negative. Okay, so what happens? At theta equals 0, the point is, at theta equals 0, r equals 2. So the initial point here is 2 comma 0 in the polar plane. Okay, so that's the point 2 comma 0 in the polar plane. As theta is getting larger, theta from between 0 and pi over 2, the value of r is decreasing. So if you start plotting, the distances are getting closer and closer to the origin. And when you get to pi over 2, the height is 1. The distance is 1. Between pi over 2 and pi, that's the angles in this sector. That's the second quadrant. The value of r is decreasing down to 0. When r is decreasing down to 0, that means that eventually, when it hits 0, you get the origin. So this is halfway across. We've handled theta going from 0 to pi. Now, what happens from pi to 2 pi? Well, from pi to 3 pi over 2, that's the third sector, the third quadrant, r is increasing from 0 to 1. So I'm indicating that here r is increasing from 0 to 1. And from 3 pi over 2 to 2 pi, that's the fourth quadrant, r is going from 1 to 2. So the distance is getting bigger and bigger and bigger to the origin. So this looks like a heart, and the name this graph is given is called a cardioid, which is Greek for heart or heart-shaped. Okay, so that is that's an example of polar graphing. Okay, let's do another one like that. So let's do the example of r equals cosine of 2 theta. So I want to, again, do the same thing I did before. I want to consider the theta axis and cosine of 2 theta vertically. So, and I didn't draw that very well. So what happens when theta is 0? So let me delineate it this way. So 0 pi over 4, pi over 2, 3 pi over 4, pi. Let me erase a little bit here because I need more space. Then it's 5 pi over 4, 6 pi over 4, which is 3 pi over 2, 7 pi over 4, and then 2 pi eventually, which I can't even put in the picture. Okay, so what's happening between 0 and pi over 4? Well, we have to take twice theta. So at 0, you have the value, the height is 1. And when you get to pi over 4, theta is pi over 4, then twice pi over 4 is pi over 2. The value of r is 0, so it's decreasing down to 0. Okay, and then from pi over 4 to pi over 2, so at pi over 2, you're going to get cosine of pi, which is minus 1. So that's down here, and it's decreasing down to minus 1. From pi over 2 to 3 pi over 4, it's increasing back to 0. From 3 pi over 4 to pi, you're going to get back to from 0 to 1, and then it starts repeating itself in the same way. Like that. Okay, so that is going to help us graph it. So let me now get a set of axes. This is the polar plane. Okay, and let me start graphing this. Okay, so what's happening with between 0 and pi over 4? So let me put in some dotted lines here. This is the pi over 4 line. Then we have pi over 2, 3 pi over 4. I'm going to make a bunch of different sectors. So let me label the sector 1, sector 2, sector 3, sector 4, sector 5, sector 6, sector 7, and sector 8. Okay, let's going on with sector 1. Well, cosine of 2 theta is decreasing from the value of 1, so that's here, down to the value of 0, so as the angle increases to pi over 4. So it's looking like this. What's happening from pi over 4 to pi over 2? That's sector 2. This is sector 2 over here. But the value of r is negative, so we go to the opposite sector when graphing. The opposite sector is sector 6, and we have to continue graphing the value of r in sector 6. So that's going to give me, R is going to go from the value of 0 to -1. So now we're here. So now we're from pi over 2 to 3 pi over 4. That's sector 3 we're in. That's here. But the value of R from pi over 2 to 3 pi over 4 is negative, so we have to go to the opposite sector, which is sector 7. And the value of R is going from -1 to 0. So the picture looks like this. Oops. Okay, so we've handled sector 3. Now we go to sector 4, which consists of angles between 3 pi over 4 and pi. Between 3 pi over 4 and pi, if we go to the black graph, 3 pi over 4 and pi, R is going from 0 to 1. So we're in sector 4, it's going from 0 to 1. Looks like that. From pi to 5 pi over 4, we're in sector 5, and R is positive, so we don't have to flip it, and R is going from 1 to 0. Okay, so now we're in sector 6, and sector 6 we're going from pi over 4 to 3 pi over 2. R is going from 0 to -1, so it's always negative in that, or non-positive in that range. So we have to go back to sector 2, which is opposite to sector 6, and R is going from 0 to 1. Now we're in sector 7. Sector 7 is from 3 pi over 2, 3 pi over 2 to did I do the, yes. Sector 7 is from 3 pi over 2 to 7 pi over 4. R is going from -1 to 0. So that means R is negative. So we have to go to the opposite sector, which is sector 3, and R is going from 1 to 0 in sector 3. Finally, we go from 7 pi over 4 to 2 pi, then R is going from 0 to 1. And this is the picture. It's not very well drawn, but it's usually called the 4-leaf rose. Okay, so that's the graph. So what I think I'm going to do with the remainder of this lecture is just pull up a chart that's in the textbook at the end of this section to show you a little bit of botany, or maybe zoology, of the different kinds of curves that occur when you graph in polar coordinates. So as you can see, there is a table here of common polar curves, and I suggest that you look at it. So what we just graphed was the 4-leaf rose, which is on row 3 of the table. It's the first entry. You have other kinds of roses, and they're indicated on the table. We also graph the cardioid, which is in the second row and the second entry of the second row. So we've also graphed the circle, which is the first entry in the first row. But there are other circles. And so I'm not going to go through this entire table, but some of the exercises require you to graph things which are represented on the table. So I think that's where we're going to end today. Have a good weekend.